Hello everyone again and welcome. I did posted notes in our WhatsApp group on the discrete random variables as well as the normal distribution. So today we are going to be looking at how we can, do most of these in using R. We did look at, the binomial distribution and the Poisson distribution, and we know the probability mass function, which is mostly used a lot for discrete random variables. So if you want to perform like just looking at the probability mass function of a binomial distribution in R, you can do d binom, and then if it is a cumulative density function, which is like calculating the probability. Since if maybe you have like 10 independent identical distributions or maybe 10 independent trials, and then you're trying to maybe calculate the probability of success. Maybe you're tossing a coin 10 times, you want to calculate the probability that you are going to obtain exactly 3 heads. That is something you can do. We call this the cumulative density function. You can calculate that probability using the p binom for binomial distribution. And then if you want to generate a random sample from a binomial distribution where you're taking maybe like n independent trials and then you know the probability of success, then you have to use the R bin. For the Poisson distribution, you use a d pois if you are going to just like look at Poisson distributions are you when you want to model cases like the number of cars that are passing through maybe some checkpoint. Those are cases you can model using the Poisson distribution, or the number of cars at the gas station. That's something you can also model using the Poisson distribution. But if you want to calculate your probability, you're going to be using p pois, and then if it is a random sample you want to generate, and then you can use the R pois. So let's start with the binomial distribution. So let's say, yeah, I have maybe trials from 0 to 10. Normally 0 to 10, that is how you can do this in R. Like you want 11 independent trials or 10, trials that you want to, maybe get the probability of success. And then you want to look at those trials and try to calculate their probabilities. Now, I'm looking at here the P being here, maybe just a binomial, which is a discrete random variable. And then K here will be the number of trials that I'm performing, which is from 0 to 10. And then I want the size, there are 10 independent trials, and then the probability of success here to be what? To be a 0.3. So here, I'm just trying to run this to see, you can see, how K looks like. If you want to look at K, we haven't looked this, we are generating, you see that we are picking a number from 0 right up to what? To 10. That's how you can do this in R, like a sequence. And then if I run this pnum, we can also look at how this pnum looks like if I want to. Just that probability p underscore bin. And then let's see how it looks like down here. You see they are just these probabilities that were calculated for each of these numbers. A binomial is like, you can calculate that using the notion, the formula. If you go through the notes, you see the formula, which is like in terms of what the combination stuff. So for p, maybe x equals to 0, this is the probability you're going to have, and so on. So we can put this in terms of a data frame just to see how it looks like. You see that for k equals to 0, we can start that this will be the probability. And then we also know that the sum of everything for this probability mass function for the any discrete random variable, that sum will always be equals to what? 1. And then you can also plot this to see how it looks like. If I want to plot this, which is like just a bar plot for those distribution, I can plot this. You can see that, this look like something like some looks like somehow the right skewed, somehow symmetric distribution. We are not certain, but that's something we can, we can just term it that way. And then if you were to calculate the probability, let's say if you were tossing a coin maybe 10 times, you want to calculate the probability that you are going to obtain exactly 3 heads. We can term this in terms of a discrete random variables, like a 0 will be no head, and so on. So if x is equals to 3, let's say that we are looking at the head, and then this is how you can calculate this in that probability in R. So it will be D bin. We have since it is exactly x equals 3, it is not, it is not a cumulative density function like within intervals. You just use D bin. Now we pass in that value 3. The number of trials, that independent trials, is 3. We already saw that the probability of success there was 0.3. So if you run this, we are going to have that probability. Remember, probability is less than or equals to 1, but greater than or equals to what? 0. And then if it is something which is like an interval, if you want to look at cases like p of x less than or equals to 3, maybe you are going to obtain um, uh, heads that are less than or equals to 3. Then in that case, you are going to be using what? The p binom rather than what? The d binom. So you have to be very careful. So here we are going to be passing our 3 normally, but we're going to have 10, and then we have that probability of success. The assignment that I'll be posting, you'll be having something like this, so you have to be very careful when you have to do this in R. So if it is something which is greater than 3, since most of the times we are mostly calculating the area under that graph to the left, so we are going to do P greater than 3 should be 1 minus what? The P num less than or equals to what? 3. So we have to note this. Like most of the times, instead of looking at P greater than 3, that means you have to pick from 3, 4, 5, 6, 7, 8, 9, and 10, right up to this number of trials that we have. So instead of doing that, we can just take P of x greater than 3 is the same as 1 minus P less than or equals to 3. And we already calculated this. So if we have this value, which is this one, we can always get that probability. So let's go to the case of the Poisson distribution, which is this. So Poisson, we can also look at range sequence from x 0 to 10, and then we generate a Poisson distribution, which is d par, which is remember here, lambda here is like the mean of that Poisson distribution. So we can run this, and then we can also look at how that Poisson looks like. We can do p underscore par, and then we run. We can just look at the way it looks like. We are looking, this value is less than 1, which is always the case. And then we can also put this in terms of a data frame just to see how it looks like, and then we can plot this. We plot this, you see it's also looking more like this distribution here. It looks a little bit symmetric, but more like right skewed. I would not say it's a symmetric distribution. And also we should note that the sum here should be approximately 1, as we have 0.999 is approximately 1. And then in the case of calculating probabilities, if it is something which is p x is equals to 4, we are going to use the d part, which is the value of lambda here is 2, and then x is equals to 4. So we run this, we're going to have that probability, which is 0.09, something like that. If it is something which is like a cumulative density function, we are going to using the pp, the p part, which is like and then we can run this, and then so if it is, we are looking at the probability of x greater than 4, it is the same as the probability. This equivalently to probability is the same as 1 minus probability of x less than or equals to 4. X less than or equals to 4. So that is why you see that I'm using 1 minus this value here, like in the case of the binomial. So another, for some of the notes I also posted, looked at the normal distribution. So normal distribution, there are cases that we really see, we are going to be looking at, especially when it comes to hypothesis testing. We might not really, when it comes to hypothesis testing, we must be using maybe the standard normal distribution, how we can, make decisions. Maybe you are trying to test a sample that you created. Maybe it is a device that you produce. You want to be sure that that device will be effective. You can use hypothesis testing to do that. Maybe you are comparing the means between two groups, or maybe an experiment that you perform. Maybe like saying that the mean of people that live in villages and people that live in town, there is a significant difference in the way they behave or something like that. You can use hypothesis testing. So we are going to be looking at that. We'll see that a lot in the next the notes that I'm going to be posting this week. So if I want to generate Now, sequence here says that, like, if I want a sequence of numbers from 130 to 210, and then I want the difference to be by point 1, I can do this in R by using what? Sequence. So if I run this, let's just see how it looks like. You are going to be generating this a lot. Maybe you don't have data, but you can know maybe the sequence that you want to generate that data. We can see that. Let's go look at it. We see that, it's starting from 130. From 130 it moves to what? 130.1, because it's adding 0.1 to each. So it goes to what? 130.2, and then we get to what? We get to the last value here, which is the 210 that we have, which is this 210. And then let's say we are looking at the height of students in a class, and those heights, I said, they are ranging from 130 to 210, incremented by 0.1. So if I want just a normal distribution, which is a probability density function of that, I will use dnum. Then we know that the range of those height, I'm assuming that the mean, I can try to calculate the mean of this, and let's see. We can do mean of x, just to be sure, mean of x. Let's see, I'm just assuming that mean, the mean is 170. And then I can also look at the standard deviation SD of x. And then, the standard deviation is like, 23. But if I want to look at the standard deviation is there, maybe like, 23 point something. So I'm just assuming that I have this distribution. I'm assuming that the standard deviation is 10, and then I want to get a normal distribution from this. So if I run this, because if you go through the node for a normal distribution, we will have the mean and the standard deviation. So if I run this and then try to look at y, we can see like random numbers generated based on what? Using the height of these students that I had from 130 to 210, incremented by what? 0.1. I can also plot this distribution. We will look at the height, and then also look at the normal distribution that I got from the height of these students using the mean of 170 and the standard deviation of 10. If I plot this, you're going to see how it looks like. You see, it's more look like the standard number, like a normal distribution, where we have the mean here as 170, and then the standard deviation as 10. You see, this more looks like a symmetric distribution. So if you look through the notes that I posted, you should be able to see something like that. Now, sometimes you might be asked to calculate like the probability of a normal distribution. In this case, we are going to be using the p-norm, and if we are looking at the probability which is less than or equals to 180, we already know that the mean is 170, and we know that the standard deviation is 10. So we'll need this to be able to calculate that probability. So if I run this, still we're gonna have that probability is always less than what? Less than or equals to 1, but greater than or equals to what? 0. Now, if I'm looking at something which is greater than 180, I say this will be the same as what? 1 minus the probability of x less than or equals to what? To 180. So that is why we are having 1 minus this value here. 1 minus p norm of this. So if I run this, so meaning that instead of just going this through this, I can just have computing this here. I can just do 1 minus this probability that I had, which is this value. If I just copy this and paste up here, you are going to have the same thing. If I paste this here and run it, you see that we are having what? 0.15, which is the same like this. So it's something you can do that way. Now, sometimes you might be asked to compute the probability of what? X is less than or equals to 180, but greater than what? 160. This is the same like what? You are calculating this probability minus what? Minus this probability, which is like what? We are having p norm, we have 180. You must sometimes, here you must not pass this mean is equals to 170 and standard deviation. By default, this function knows that when you pass this value of that probability, the next thing should be the mean, and the other one should be what? Should be the standard deviation. That is why here I don't really care about that. So if I run this, I should have that probability. So You have to take care, watch this video, and I'm going to be posting the next assignment, which will be mostly based on these concepts. The next video that we are going to be looking at will be how we can generate maybe like a random normal distribution, and then try to maybe look at whether there is a difference in between the means of those two random distribution, which is the case of what hypothesis testing. Thank you so much, guys, and keep following for more tips in R programming and introduction to statistics. Bye for now.